We come to the end of this notebook with a revision of the decibels. So we'll go through an experiment, and in this process we will investigate different characteristics of the decibels and many other things. So in this experiment we will have two input signals. So we'll have a sine wave with 50 Hertz and an amplitude equals to 2, and we will pretend this for example our voltage values, and we will have a cosine with 2 kilohertz and the amplitude of 10, and we will add these two signals. When we see we have our sine wave, so I'm plotting just the one period of the sine wave, and then we have our cosine with amplitude of 10 and our sine wave with amplitude of 2, and when we add these two signals we have this input signal here. So then we will take the FFT of this input signal, and here I'm having the FFT that now I'm using 2 to the power of 16 a number of FFT points. I'm calculating the magnitude. I'm compensating here for the number of FFT points and the frequencies on the negative frequencies. So when I plot the magnitude of the FFT, we have here our two components, one at 50 Hertz, another one at 2000 Hertz. So we have here a magnitude of almost 10. But here we already see that our magnitude is 1.5. So this is due to the scalloping error. So it happens, the FFT here has a limited number of FFT points, and depending where your frequency is located, maybe it's not in the center of the beam, but it's in the middle of two beams, and we have this error in amplitude. So bear in mind that when we don't have any window, we are in fact using rectangular window, and the rectangular window has certain characteristics in frequency. So what we can do is we can use windowing, and a very good window to estimate the amplitude of sine waves in the frequency domain is the so-called flat top window. So what I'm going to do here is I'm creating this flat top window, and then I am multiplying our signal in time domain with this window. Then I'm taking the FFT of the windowed input signal, and here I taking into consideration also the window, and now we have here our new windowed signal. So the magnitude and also in dB scale. So now the same signal but a windowed version of this signal, and we see now we have 2 at 50 Hertz and 10 at 2000 Hertz, which were the original amplitudes of our input signal. And now we come in the dB scale. So we will take a reference as 1 voltage. So we had an amplitude of 2 volts. In the dB scale, it will represent by 6 dB. If we have 10 volts in the dB scale with a reference to 1 volt, we have 20 dB. So we can already see that there is a ratio of 2. So 2 volts and our reference voltage is 1. So we get 6 dB. And when we have 10 volts and the reference voltage is 1 volt, we have 20 dB. So let's go back and revise the dB. So dB is a ratio, and now we have two different equations depending if we're dealing with voltage or if we're dealing with power. So usually we can have power is proportional to the voltage squared, and this is why we have this difference. So the equation for voltage is 20 log 10 of V2 divided by V1, and SimPy already transforms this log 10 as to natural logarithm in the base of natural logarithm. So it gets a 20 log of V2 or V1 divided by log 10. So this is what SymPy already simplifies the logarithms in the base 10 to 2 division in logarithms of natural logarithms. So, and we see the biggest difference here is that we have 10 log for power and 20 log for voltage. So if we have our values here and we solve these equations, we will see that, for example, when the amplitude is 2, and then our reference voltage is 1, our voltage is 2, and then we have 6 dB as we seen here. So we had 2 here and we have 6 here.